In the last two lectures, we have discussed two important applications or examples of calculus of variations. In fact, now we are going to discuss a very important problem regarding this. Actually, this problem is the problem of Brachistochrone. You know, the word Brachistochrone means what? In fact, this word is a French word which is made up of two words. Brachistos means shortest and chronos means time. So this word means shortest time. In fact, in this problem, we find a curve joining 2 points along which a particle falling from rest under gravity, neglecting the resistance of the medium, travels from higher to lower point in the minimum time. So our problem is to find the path followed by the particle falling under gravity without any resistance, the path for which the time will be minimal. So let us consider for this a xy plane where I have considered the x-axis in vertically downward direction and y-axis in horizontal direction. And let us consider that a particle is falling under gravity freely from rest. You can see this figure. I have considered that this point 1, whose coordinates are x1, y1, is the initial position from where the particle will start to move from rest under gravity, and 2 is its final position, and a curve connecting these 2 points 1 and 2 have been shown in this figure. You can see. Now to solve this problem, let us consider at any moment of time t, the particle is at this point P on this curve, whose coordinates are x and y. And the velocity of the particle at this moment is v, as I have shown in this figure. Now, if you consider that this particle traverses a very small distance along this curve, which is ds, in a very short interval of time dt, then you can consider this velocity v as constant for that very short interval of time. So you can see what will be the time taken by the particle in traversing that distance ds. For your convenience, I am just writing in very short what I have told you regarding this. So let us consider a curve. Let us consider a curve connecting points 1 and 2, followed by the particle, In fact, the particle has been released from this point 1 from rest, and at any moment t, as I have told you, the particle is at this position P where its speed is v. At a time t, the particle is at p xy and its speed is v. And we have considered that this ds is distance covered by the particle along the curve between time t and t plus dt, let us say. Then you can see what will be this time dt. This time dt is actually the time in which the particle has covered this distance ds. So you can say this time dt will be what? This will be ds over v. ds over v. Let us say this is equation 1. Now, as you can see, the particle is falling under gravity without any resistance. So we can use the equation of motion of the particle falling under gravity freely when acceleration due to gravity g is constant. So now you know that v square is equal to u square plus 2gh. But here u is equal to 0 because the particle falls under gravity from rest. So its initial velocity is equal to 0. And at the same time you can see what is this h. H is actually the distance covered in downward direction by the particle, and you can see this is actually x. So h is equal to x. Therefore, you can say that this v square is simply equal to 2gx. Actually, this result can also be obtained by using the principle of conservation of energy, and you will get the same result. So this implies v is equal to a square root of 2gx. And again, you can see what is this ds. You know ds is equal to dx square plus dy square whole to the power half. You have used this result several times. So now take this dx square as a common factor. This will be then 1 plus dy by dx whole square and whole to the power half dx. And this can be written as 1 plus y prime square whole to the power half dx. Here you know this y prime has been written instead of dy dx. Now let us substitute these two values, that is the value of v which is root over 2gx and value of ds which is this much in this equation 1. So after substituting these two values in equation 1, you will get the time dt which the particle takes in covering this distance ds along the curve. So therefore we can write dt will be equal to 1 plus y prime square whole to the power half dx and over root 2gx. This is actually the time taken by the particle in covering an elementary distance ds. So if you want to calculate the total time taken by the particle in moving from this point 1 to this point 2, you can easily calculate it simply by integrating this result. So you can see what will be actually the total time taken. So you can say, so the total time taken by the particle in moving from the higher point 1 to the lower point 2. What will be that time? You can say that if we denote this time by t12, then this will be simply integral of dt from 1 to 2, and that will be equal to integral from 1 to 2 1 plus y prime square whole to the power half dx over root over 2gx, and you can write this equal to integral from 1 to 2 f of y prime x dx. So from this equation we can recognize what is this functional f. Therefore you can say this f of y prime x is equal to what? You can see this is simply equal to 1 plus y prime square whole to the power half over root over 2gx, and we can write this 1 plus y prime square over 2gx and whole to the power half. So this is the functional f. Now you know for this time t12 to be minimum, this f must satisfy the Euler-Lagrange equation. So now we will apply the necessary condition for t12 to be extremum. So you can see what will be actually that condition. So you can say for t12 to be minimum, you know the Euler-Lagrange equation must be satisfied. It means what? You know what is Euler-Lagrange equation? This is in fact d dx del f by del y prime minus del f by del y equal to 0. Now let us substitute the value of f in this equation, and you can see here what is this f. We have already obtained the value of f here in this equation 2. So now we will substitute this value of f in this equation. So you can see this is d dx del y prime, and f is what? F is actually 1 plus y prime square over 2gx whole to the power half, and minus del y, and again f is 1 plus y prime square over 2gx whole to the power half, and this is equal to 0. Now let us simplify this equation. See here, this is d dx, and now we will differentiate this function partially with respect to y prime. So as you are differentiating it partially with respect to y prime, so x will be treated as constant, and so this will be simply 1 over root over 2gx, this is a constant factor, and differential coefficient of 1 plus y prime square whole to the power half will be what? This will be 1 over 2 root over 1 plus y prime square times 2y prime, and minus, see here, as we are differentiating partially with respect to y of this function, but this is not a function of y directly, so its partial derivative with respect to y will be 0, and so this is 0 and this equal to 0. Now you can see this 2 and this 2 will cancel out, and our result is d dx y prime over root over 2gx times root over 1 plus y prime square, and this equal to 0. So you can see that as derivative of y prime over root 2gx times root 1 plus y prime square is 0, so definitely this should be a constant. So you can write therefore that y prime over root x times root over 1 plus y prime square equal to constant. I have omitted root over 2g because root over 2g is already a constant. So if you will multiply this constant by root 2g, then that will be another constant. So I have omitted that. Now let us square this equation both sides and say this will be y prime square over x times 1 plus y prime square, and this will be equal to some another constant. Let us say this constant is c. Now we will simplify this equation. You can see after cross multiplication we will have y prime square equal to c times x times 1 plus y prime square, and this may be written as cx plus cx times y prime square. Now let us bring this term in LHS and take this y prime square as a common factor, then this will be 1 minus cx, and this equal to cx. This will be equal to cx. Now you can see that this equation can be written as y prime square times 1 over c minus x equal to x. Actually I have divided the LHS by this c in RHS, so you can write in this way this equation. So now let us see here, if we actually multiply both sides of this equation by x, what will be our result? You can see this will be y prime square times x over c minus x square, and this is equal to x square. What we have done? Actually we have multiplied this equation both sides by x. So now from this equation you can easily find what will be y prime. So you can see this y prime will be equal to x over root over x over c minus x square. Now to obtain the value of y, let us put here c equal to 2a. This is for convenience in integral. 1 over c equal to 2a. So let us put 1 over c equal to 2a. This substitution is made for convenience. So you can see now what will be our equation here. There is y prime equal to x over root over x by c minus x square, and 1 by c we will now write 2a. So this will be 2ax minus x square root, and y prime is dy by dx. So you can write that dy by dx is equal to x over 2ax minus x square root, and from here you can write integral of dy. This will be equal to integral of x dx over root over 2ax minus x square. Now you can do this integration by using a lot of algebra, but I am writing the standard value of this integral here. So you can see this will be y equal to a cos inverse 1 minus x over a minus 2ax minus x square whole to the power half plus some another constant, let us say c prime. So this c prime is another integration constant. In fact, if you consider this c prime equal to 0, then for x equal to 0, this y will be also 0. So I have considered in the figure the value of x equal to 0. So if we consider if c prime equal to 0, then y will be equal to 0 for x equal to 0. It means the particle if you consider that the particle has been dropped from the origin, then actually this c prime will be equal to 0. So now let us consider the initial position from when the particle is dropped and it moves under gravity is the origin. So in this condition, what will be our equation? And now this c prime is 0. So you can write in this condition, y is equal to a cos inverse 1 minus x by a minus 2ax minus x square whole to the power half. So this is actually the equation of the curve which will be followed by the particle when it takes minimum time to move from the initial position 1 to 2. Actually, this equation represents an inverted cycloid with the base along the y-axis and the cusp along at the origin. So this equation represents an inverted cycloid with its base along y-axis and cusp at the origin. So you can say that a particle falling under gravity follows a cycloid if time taken by the particle is minimum. So you have seen that how this problem of Brachistochrone has been solved by using the technique of calculus of variation, particularly the Euler-Lagrange equation. And so after this example, I hope you have been definitely familiar with the solution of the problems of calculus of variation.